Welcome to part 2 of the math behind the 555 timer formulas. I'm Dr. Plague. In the first video, we looked at the first 4 of the 5 formulas that I want to derive for you. In this video, we'll derive the last formula, which I refer to as the monster formula. This one was the new time low formula with R3 added into the discharge line. We'll be using a different technique to derive this formula. Specifically, we'll use a Laplace transform. But before we derive the monster formula, we'll go back and rederive the first time low formula using the Laplace transform to help you understand how it works.
Great! Another math video. I think I'll just go watch TV.
Hey, you never know, this could be a lot of fun.
Only for you. I'll pass.
Anyway, I'm gonna get the whiteboard ready and I'll see you right after this. So, I want to start with the first time low formula from the last video and show you another way to derive it. This time, using the Laplace transform. Remember the time low formula was the natural log of 2 times R2 times C. Now, the first thing I want to do is to convert the circuit we had into the S domain. If you're not familiar with the S domain, you can think of it as an extended or complex frequency domain, and it gives information about both steady state and transient responses. But that's a subject for another video. When we perform a Laplace transform, it converts the time domain into the S domain. Now, why would we want to do that? Well, some operations are easier to perform in the S domain than in the time domain. For example, let's suppose we want to perform convolution in the time domain, and if you're familiar with convolution, you'll know that this may not be a very fun thing to do. Well, luckily, convolution becomes multiplication when we convert it into the S domain. So, if we don't want to deal with convolution, we could convert the problem into the S domain, then simply perform a multiplication, then convert it back to the time domain. We do this using the Laplace transform and the inverse Laplace transform. Now, let's take a look at different circuit elements and see how they are represented in the S domain. Let's start with a resistor whose impedance is not dependent upon frequency. Because its voltage is directly proportional to its current, it remains unchanged in the S domain. We just leave resistors as is. Capacitors are represented by 1 over S times C in the S domain. This is its impedance. And if there is an initial voltage across it, we can represent that as a voltage source in series with a value of V of 0 over S. You could also represent the initial voltage as a current source in parallel with the value of C times V of 0. Pay attention to the polarities of these sources. Now, if you had an inductor, the equivalent of that in the S domain is S times L, and this is its impedance. You can indicate an initial current through it as a voltage source in series with a value of L times I of 0. You can also use a current source in parallel with a value of I of 0 over S. Again, pay attention to the polarity as this is opposite from the capacitor. Finally, voltage sources can be represented by the voltage divided by S. Now, in our original circuit, we had a resistor, and that remains unchanged. We also have a capacitor, and we know it has an initial voltage of 2/3 VCC, so I'll choose this representation in the S domain. By the way, you may commonly see a minus sign or sometimes even a plus sign after the 0 in this V of 0. This is if V of 0 is ambiguous, meaning a discontinuity at 0, but we're not ambiguous, so I'll skip the sign. We may have a kink between charging and discharging, but certainly no discontinuity. This voltage here could be represented by V of t in the time domain, so I'll just change it to V of s in the s domain. Beautiful. Now, let's come up with an equation. Let's use the ground node as our junction for Kirchhoff's current law. Impedances can be used with Ohm's law. So, in the S domain, the current through the capacitor is the voltage across it divided by its impedance, which is 1 over S times C. The voltage across the capacitor is V of S minus V of 0 over S. Ohm's law states that the current through a resistor is the voltage across it, V of S, divided by its resistance, R. Now, our equation becomes V of S minus V of 0 over S, all divided by 1 over S times C, plus V of S over R equal to 0. Let's solve this for V of S. First, I'll multiply the numerator and denominator of the first term by S times C. This will be the same as multiplying by 1, since SC divided by SC is 1. The denominator will disappear since SC multiplied by 1 over SC is 1. We'll multiply the SC through the numerator, giving us V of S times SC minus V of 0 times C, since SC divided by S is just C. Now I'll add V of 0 times C to each side of the equation. Let's factor out V of S. Now I'll divide each side by SC plus 1 over R. I'll multiply the numerator and denominator on the right side by 1 over C, which will be the same as multiplying by 1. This will turn the numerator into 1 and the denominator into S plus 1 over RC. Now, in the time domain, this becomes V of t equals V of 0 times e to the negative t over RC.
Okay, I'm so confused. That e just came out of nowhere. This makes no sense.
I thought you were watching TV.
I secretly want to become a math whiz.
Really?
Just kidding.
You mean you don't want to be a math whiz?
Keep it down in there. I'm watching TV.
Well, I guess I need to explain the E. To convert the equation in the S domain into the time domain, I used the inverse Laplace transform. An easy way to do this is to use a lookup table containing common Laplace transforms. This is a lot easier than calculating a Laplace transform, which, by the way, is f of s equal to the integral from 0 to infinity of f of t times e to the negative st dt, where s is a complex number. In a university course, you will usually first be taught to do this by hand. Then they teach you to use lookup tables. One place you can find a table of Laplace transforms, at least as of the time I filmed this, is to look up Laplace transform on Wikipedia. You should be able to find this here table on that page. You can see it contains functions in the time domain and the S domain. What we want to do is to try to match our terms with functions in the S domain column. So we manipulate our equation until we can match something in the table. For example, our S domain equation contains 1 over S plus a constant. Let's see if we can match that with something in the table. Let's look at the row for exponential decay. You'll see that it has 1 over S plus alpha. Alpha can be any constant. In fact, it can be 1 over RC, so we have a match. Now, taking the inverse Laplace transform, or going back to the time domain, gives us e to the negative alpha times t, all multiplied by u of t. For this, we could ignore u of t. It's just a Heaviside step function, which has a value of 0 when t is negative and a value of 1 when t is positive. We're never going to use a negative t because, after all, if you've seen the movie Back to the Future, then you'll know that bad things happen when you go back in time.
Bad things also happen when you go forward in time.
Go back to watching your TV. Anyway, that's why in the integral I had the lower limit set to 0 to indicate a unilateral transform. since we're not going back in time. So we can write the transform like this. E to the negative alpha t transforms back and forth to 1 over s plus alpha. V of 0 is just a constant coefficient, so that can just carry through in the transform. And 1 over RC will take the place of alpha, so we can transform this into V of 0 times e to the negative t over RC. Now, we just need to add our initial and ending voltages and solve for t. Our initial voltage will be 2/3 VCC, and we want to know the time when the capacitor discharges to 1/3 VCC. I'll divide each side by VCC, then multiply each side by 3. Now, I'll multiply each side by e to the t over RC. This will get rid of e to the negative t over RC. Now, I want to take the natural log of each side. Since natural log is the inverse function to e, it will cancel out the e and we're left with t over RC equal to the natural log of 2. Now we can multiply each side by RC. And since R represents R2, the time low is equal to the natural log of 2 times R2 times C. Remember that when we derived this in the time domain, we had a differential that we had to take care of and we had integrals to solve? Well, we were able to bypass all that by using a Laplace transform, which is one of the advantages of doing it this way. Now that we're familiar with the Laplace transform, let's take a look at the monster formula and see how I derived it. Let's set this problem up. The time low occurs when the capacitor is discharging, and during that time the discharge pin is pulled to ground, which grounds this side of R3. We can consider the threshold and trigger pins on the 555 as high impedance inputs. Therefore, we don't need to worry about their effect in the circuit. Because of this, we can redraw the time-low circuit like this, where V of t is the instantaneous voltage across the capacitor. Now, I want to convert the circuit into the S domain. As I explained before, the resistors remain unchanged. VCC will change to VCC over S. The capacitor will be represented by 1 over SC in series with a voltage source of V of 0 over S, where V of 0 is the initial voltage of 2/3 VCC across the capacitor. V of t can simply be changed to V of S. We're going to use a method of mesh currents. Since we have 2 meshes here, I'm going to draw in 2 mesh currents, I1 of S and I2 of S. Now our circuit is converted to the S domain. I would like to write an equation for V of S, but I'll need to know what I2 of S is. So let's work towards that. Since we have 2 meshes, I'm going to use Kirchhoff's voltage law, which states that the sum of the voltages around any closed loop is equal to 0. I'm going to draw in the polarities of the resistors. Since the mesh currents through R3 are opposite, R3 has 2 opposing voltage drops, one for I1 and one for I2. Bear in mind that I use the passive sign convention when summing up voltages in a loop. This means that voltage drops across resistors are positive, and voltage sources are negative if current flows into the negative terminal. Many people use the active sign convention, where a voltage drop is negative and a voltage rise is positive. With the passive sign convention, you just use the sign that the current flows into. For example, I1 flows into the negative terminal of VCC, so that voltage in the loop will be negative. By the same token, I1 flows into the positive side of R1, so the voltage across R1 will be positive. It doesn't matter which sign convention you use, just be sure you are consistent. Now, using Kirchhoff's voltage law, I'll write an equation for the first mesh with I1 of S. The voltage across the source will be negative VCC over S. Voltage across the resistor is current times the resistance, so for R1 it is I1 of S times R1. The voltage across R3 will require both I1 and I2, so we'll add I1 of S times R3, And since I2 travels through R3 in the opposite direction, we'll subtract I2 of S times R3. Then we'll set this all equal to 0. Now I'll write an equation for the second mesh with I2 of S. R3 has two currents through it, so we have I2 of S times R3 minus I1 of S times R3. Then the voltage across R2 is I2 of S times R2. Then the voltage for the capacitor will be I2 of S times 1 over SC plus V of 0 over S. And this is all equal to 0. Now, I want to solve the second mesh equation for I1 of S. And to do this, I'll first swap the first two terms and solve for I1 of S times R3. Then I'll factor out I2 of S. And finally divide each side by R3. Now I'll take the first mesh equation and solve for VCC over S. Then I'll factor out I1 of S. Next, I'll substitute in our mesh 2 solution of I1 of S. Now, since this is looking pretty hairy, I'll go ahead and create two more reference designators, R4 and R5, where R4 is R2 plus R3 and R5 is R1 plus R3. Then I'll substitute them into our equation. We just need to make sure that we substitute them back before we're done with this derivation. Next, I'm going to multiply R5 through the numerator. Then I'll separate the first term on the right side into two terms. I'm going to rearrange the sides while subtracting the second term on the right from both sides. Then I'll multiply the S into the denominator in the last term. I'll multiply VCC over S with R3 over R3, which is the same as multiplying by 1. And I'll factor out I2 of S and multiply R3 by R3 over R3. Again, this is multiplying by 1. I'll add these terms together, then multiply both sides by R3. Next, I'll divide each side by this here. And I'll cancel out R3 since it's in both the numerator and the denominator. I'll multiply S through the denominator and cancel out this S. Now we have a solution for I2 of S. And now we can write our equation for V of S, which is I2 of S times 1 over SC plus V of 0 over S. Now we can substitute in our solution for I2 of S. I'm going to finagle this until I get something in the form of what we have in the S-domain column of the Laplace transform lookup table. We can see that V of 0 over S is some constant times 1 over S. And 1 over S exists in the lookup table, so we just need to finagle this part. I'll multiply R5 through in the denominator, and then multiply C through it. I'm going to swap these two terms and factor out an S. It looks like we are getting close to this here, so let's see if we can finagle it a little further. I can divide both the numerator and denominator by this here. I'll multiply the numerator by R5 over R5, which is equal to 1, and separate it as follows. Now, we could use this here transform pair to perform an inverse Laplace transform. And we can use this transform pair on the last term. So, in the time domain, V of S becomes V of t, and this fraction is a constant, so we can keep it as is. Now, we can substitute in this for alpha, and we have this. Since 1 over S transforms to 1, V of 0 over S just becomes V of 0. And there's our transform. Now I want to substitute in the initial voltage, which is 2/3 VCC. And we want to know the time when the voltage drops to 1/3 VCC. Now we just need to solve this for t. So I'll divide both sides by VCC. Then multiply both sides by 3. Then subtract 2 from both sides. I'll multiply both sides by R5. Then divide both sides by 3R3 minus 2R5. Next, I'll negate each side, then swap sides and add 1 to each side. I'll rewrite the 1 as this here. Since the numerator and denominator are the same, it is equal to 1. Now I'll add the right side together and add R5 to negative 2R5. I'll take the reciprocal of both sides, then I'll take the natural log of both sides. And you probably know by now that the natural log cancels out the e. I'll multiply both sides by the denominator from the left side, and divide each side by R5. I'll substitute R4 back to R2 plus R3. And then substitute R5 back to R1 plus R3. I'll clean up the natural log a little bit, then multiply the two binomials together. Next, I'll finish cleaning up the natural log. Now I'll factor out a c. Then I'll remove these parentheses. These R3 squareds cancel out. Then I can swap these two terms so I can factor out an R1. And this is the formula for time low with R3 added into the discharge line. Well, I hope you've enjoyed this little introduction into the Laplace transform. Thanks for watching. Please peck at that like button, subscribe if you haven't already done so, and I'll see you next time, right here on Dr. Play.